Alright, so identifying minerals. In order to identify a mineral, figuring out exactly which one it is, we use some tests. That includes some amusing names like streaking and cleavage, luster and hardness, and also the familiar density. All of these characteristics, though, depend on the atomic structure of the compound. Well, what does that mean? Well, think about diamonds. Diamond is pure carbon. So is pencil lead, graphite. These are both chemically the same. They're both, the chemical formula you see on the bottom here is C for carbon, pure carbon. However, no one is ever going to confuse a diamond with graphite. You don't use a diamond in your pencil, and you don't wear a piece of pencil lead on your finger. They would not be an attractive piece of jewelry. It would get very messy. Diamond is very hard, which makes it good for jewelry. It's usually see-through. It does not scratch easily. We use it for jewelry, and since it is so hard, we use it for cutting and drilling. And you can see graphite, though, looks very different. It's so soft your fingernail can scratch it. It's slippery, and it's metallic looking. It's good for drawing, and since it's slippery, it's good to actually lubricate locks. If you have a sticky lock at home, you spray some graphite powder in it. What makes these two different is not just what it's made of, but how the atoms are arranged. You see in the left here, the diamond is a very clear crystal. It's a very rigid structure, three-dimensional structure. And it's very different from on the right, graphite. It forms these long sheets, and these sheets slide against each other. That's what makes it so slippery, and that's also what makes it easy to scratch, because one sheet, just like if you've ever accidentally knocked over a sheet of papers, they move pretty freely on each other, whereas this on the left does not move. So the atomic structure of the mineral is very important for making it unique. The different crystalline structures you can see here, you don't need to memorize them, but you should be aware that there are several different ones. My favorite is the hexagonal at the bottom here. It's the same shape as a pencil, actually, a traditional pencil. But it's the actual crystal is how quartz grows. And quartz grows and looks like little pencils. It's kind of pretty. The first technique we use to identify a mineral is luster, and it's how light reflects off the mineral. The luster can be metallic or non-metallic. Metallic means it reflects light like a metal. It's opaque. All the light is reflected. None of it goes in. You can't see through it at all. You can see some examples here that you're familiar with: gold, copper. You may not be familiar with iron pyrite, fool's gold. This galena is one of my favorite minerals. It's sort of a silver color. Now, not all samples will look so bright and shiny. Sometimes they will be tarnished, just like coins do. And if you're trying to figure out if a mineral is metallic or not, and you can't tell just by looking at it, I mean, it's not like this emerald on the right. That's very clearly not a metal. But if you have one you're confused about, gently streak it, and I'll talk about what that is soon. Metals tend to have a dark blackish streak even when you rub them very gently on a streak plate, so that's a good sign something's metallic. Non-metallics tend to be glassy. That would be like emerald or quartz. Adamantine is the special name for the brilliance of a diamond. Turquoise, you can see, is waxy. Limonite is dull and earthy. Muscovite is kind of neat, breaks into thin sheets, kind of like graphite did in the structure, but on a larger scale. And it's actually completely see-through. It's kind of like the darker version, biotite, is a lot like sunglasses. But these are all different types of non-metallic lusters. Specific gravity is also a way we can identify a mineral. This is a comparison between a mineral's weight in air and its weight in water. It's basically a measure of density. Why is that important? Well, some things are more dense than others. For example, galena, this metallic one, is lead sulfite. And as you can imagine, since it's got lead in it, it is very heavy for its size. It has a specific gravity of 7.5, which is entirely different from bauxite, this odd-looking mineral on the right. It's actually, believe it or not, what we get aluminum out of. We have to melt that to get aluminum. Pretty cool. But aluminum is a much more lightweight metal with a specific gravity of 2.3. We can identify minerals in part based on their specific gravity or their density. Color, though, is not a way we want to identify minerals. The same mineral can come in many different colors. For instance, quartz on the left can be clear. It can be purple, in which case we often call it amethyst. It can be brown, in which case we call it smoky. It can be pink, in which case we call it rose quartz. But they're all quartz, so you can't say, oh, it's clear, it must be quartz. Might be diamond, might be calcite, might be salt. You don't want to mix them up. On the right, we've got beryl, and these include emeralds and aquamarine and many different shades you can see here, but they're all the same mineral. So don't depend on color as a way to identify a mineral. Now we have streaking. This is a form of color that is important. It's the color of the powdered form of the mineral. You can see this rock has gently been rubbed against this unglazed ceramic tile, and it created this blackish powder, which is an indication, if it was rubbed lightly, that this must be a metallic mineral, even if you can't quite tell from the image. Some minerals are so hard they won't leave a mark on a scratch plate. In that case, you don't have to worry about the color of the streak. But streak can be really interesting to identify some metals and some of the softer minerals. Next we have hardness. Now hardness is not whether it's saying that it doesn't break. Hardness is the resistance of a mineral to scratching. You can see here a piece of quartz is being used to scratch this glass. That's indicating that the quartz, since it can scratch the glass, the quartz must be harder than the glass. Friedrich Mohs put together a hardness scale, and he ranked minerals on a scale from 1 as the softest to 10 as the hardest. The higher the number is, the more other minerals it can scratch. Diamond is the hardest. It has a number 10, so it scratches anything with a lower number. Talc is a number 1. It can be scratched by everything above it. Fluorite is a 4. It scratches calcite, gypsum, and talc, but is scratched by apatite, feldspar, and quartz. Though keep in mind, though, hardness is not about breaking. It's about scratching. Diamonds actually shatter very easily. You probably know a woman who's broken her engagement ring diamond by accident, because they do shatter very easily, especially when it's cold. But you could use that diamond ring to slice up a steel knife. Some basic ones that you need to know the hardness of. A fingernail typically is about a 2.5, so between calcite and gypsum. So you could scratch gypsum and talc with your fingernail. Talc, by the way, is what we use to make baby powder, talcum powder, and gypsum is what's in the drywall of your house at home. Glass is a 5.5. Now, testing hardness is very important. First thing you want to do, because you don't want to destroy your fingernails if you don't have to, is test on glass. You lay a piece of glass flat on the table, and you take the edge of your mineral and scratch it hard against the plate. You don't want to be gentle. You can be too gentle. You can't be too hard. In other words, you can press down as hard as you want here. Please press down really hard. If you don't, even something like a diamond wouldn't scratch the the glass if you're being too gentle. But no matter how hard you scratch, a penny won't scratch the glass because a penny is softer. So you scratch it against the glass. Keep in mind that you're trying to do it hard, and see if it leaves a mark. If the mark doesn't wipe off, then your mineral is harder than the glass. So it must have a hardness. If you look over here, if it scratches glass, its hardness is greater than 5.5. We consider that hard. If the mark wipes off, or it doesn't leave a mark no matter how hard you try, that means it must be softer than the glass. So it's something below 5.5, but you need to determine what. So now you do the fingernail test. This is a mineral sample, happens to be talc, it's what we make baby powder of, and you can see she's putting her fingernail against it, and you do one side to side. You're not trying to scratch and get lots of it under your fingernail. You're trying to go side to side, see if you can make a mark. If you scratch the mineral, it must be softer than your fingernail. It's less than 2.5, and it's very soft. If your fingernail cannot scratch it, or it can scratch your fingernail, then you know it's above 2.5. You can do the same test with a penny as well. If you want more help on determining hardness, there's some links at the end of this to some really good demonstrations on YouTube. Now, breaking is a totally different thing than hardness. When you break something, the mineral either has cleavage or it has fracture. Cleavage is when a mineral breaks into flat surfaces, which is kind of unusual. You don't usually see most materials you walk around with breaking into flat surfaces. They tend to break into irregular surfaces or curved surfaces. Think of the last time you dropped a glass and it shattered. It didn't have flat surfaces. So, on the left here, you can see a piece. This is halite. It's distinguishable by its cubic cleavage. It broke into flat surfaces. In fact, it kind of looks like somebody's carved perfectly little boxes all over it. But that's the way it breaks. This is really good cleavage. It's very clear. You can even see where it's been fractured inside by a drop. Whereas on the right, these have fracture. There's no pattern that you can see. It's all rough and uneven. There's no flat surfaces. So to test, you would look at it in the light and see if you can get a reflection off of a perfectly flat surface. Keep in mind that glass-like minerals will always have reflection, but you're looking for a perfectly flat surface. Any perfectly flat surfaces indicate cleavage. The way you remember it is cleavage actually comes from the old word to cleave, which means to split, to divide evenly, or to split apart like this piece of wood. It produces a fairly flat break. That's what cleave means, and cleavage means a flat split. Whereas fracture is like you fractured your leg, you broke your bone. That's a fracture, and it's uneven. So let's look at some different types of cleavage. First, we have basal cleavage, and this is when it breaks in one direction, and it does flat surfaces like this. Mica, it is an example of this. Muscovite and biotite. It breaks into thin, flat sheets. This is breaking in two directions to create some blocks. Okay. It's flat here, but it's not necessarily, it's kind of irregular over here, so that's a blocky cleavage. Here is very clearly boxes, cubic, halite, rock salt, breaks this way. And this one here also breaks in three directions, but they aren't 90-degree angles like the halite. They're a rhombus shape. That is more likely to be calcite. You want to know the difference between these. This is probably the biggest, most important one. Halite is salt. You know, the stuff you put on your French fries. Calcite is concrete. not something you want to put on your French fries. So when you're looking at the minerals, even though they do actually look a lot alike in many samples, you need to make sure you can tell the difference between a right angle and not a right angle. Because a right angle is the right stuff to put on fries. If it's not a right angle, it doesn't go on your fries. So here's some examples. First we have this one here. You can see some sheets it breaks into, and you can even see through it. Kind of looks like sunglasses. That is cleavage. Specifically, that's basal cleavage. This one here, you can see flat surfaces here, and it kind of, those are at 90-degree angles, so that is cubic cleavage. Here, there's no flat surfaces. In fact, it looks curved, and so that is fracture. This one here, nothing flat, that's fracture. This one here, ooh, we've got a nice flat surface right here. We don't see great flat anywhere else, so it's actually poor cleavage. Here, the yellow, no flat surfaces, that's fracture. Here, well, that's very clearly cubic cleavage. This one, that's the basal cleavage again. This is another cubic cleavage. This one, no flat surfaces, so that's fracture. Down here in the bottom left, no flat surfaces, so that's fracture. This, it's all bumpy, there's no flat surfaces anywhere, so that's fracture. This one is cleavage, but notice it's not at 90-degree angles like those two, so this is rhombus cleavage. This one, 90-degree angle, cubic cleavage. And this one just looks like wood. It's actually what we call a splintery fracture. There is one type of fracture you must know, and that's this one, this curved one. It's the way glass chips, if you've ever chipped the edge of a drinking glass. It's called conchoidal fracture, and it's thought to look like a clamshell, thus the conchoidal fracture. Other properties we use to identify minerals include magnetism. If it's attracted to a magnet or messes up a compass, then it means it must have some iron in it, so it's magnetite or pyrite. If when you put it over letters it creates this doubling look, that's called double refraction, and that is a sign of calcite. Fluorescence is pretty cool. If you put your mineral in a black light, a UV light, it will glow if it's fluorescent. Fluorite, which we get because of that name of fluorescence, is the most well-known example of a fluorescent mineral, but also rubies, diamonds, calcite, and opal will fluoresce. Reaction with acid is a fun one. Here we have some hydrochloric acid being dribbled on this unknown mineral sample, and notice it bubbles up. What's happening is this mineral sample contains calcite, which is calcium carbonate, CaCO3. When it hits HCl, the carbon dioxide, CO2, is released, which is what makes it bubble. So whenever you see this bubbling, I want you to think of calcite and realize that that is actually what we use to make our concrete out of. Our concrete reacts with acid as well, so we don't want to use it in areas with a high degree of acid rain. Another example is salty taste, which is evidence that it is halite, rock salt, looks like this. But please do not test your halite samples at school for saltiness. You don't know how many people have touched them, and it would be the equivalent of licking all of their hands, and licking the floor, and licking the table, and also licking the acid. Because, again, calcite, not this particular one, but calcite often looks a lot like halite, so people will drop acid on the halite to see if it reacts. It doesn't. But you'll have what looks wet on the surface, but it's really acid. You don't want to taste that. Strong smell, sulfur. You can see here it looks kind of like cooked egg yolks, and once you've smelled it, you will know it. Especially if you get a bit of powder. Streak it a bit, that will definitely get you the odor. And finally, some minerals are radioactive, meaning that they release some radioactive energy, which can be detected by a Geiger counter. And a good example of this is uraninite. So that is how you can identify minerals and what minerals are.